Hello everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, I go through this AQA topical A-level series. This is a topic called chemical equilibrium or chemical equilibria as plural term there. So in this first question, we have this hydrogen that is produced from methane. So we know that the hydrogen that we get in Haber process, we actually get it from methane. And this is methane reacting with steam to give us carbon monoxide and hydrogen gas there. So in the first stage, this is the reaction, it's reversible reaction, use Le Chatelier principle. So Le Chatelier principle said that if you change something to a system in equilibrium, if you introduce a change to a system in equilibrium, the equilibrium, which is the system, will try to oppose the change, counteract the change, go against the change in order to return back to a new equilibrium. So whether you want a high temperature or low temperature, this is for the highest equilibrium yield of hydrogen. So that means you want to favor the forward reaction. You want to favor the equilibrium to the right hand side. So that means that do we want high temperature or low temperature? We look at the forward reaction enthalpy change. It's positive. And when the delta H is greater than 0, it means that your reactants must have absorbed energy from the surroundings, which means that the forward reaction is endothermic. The enthalpy change is positive there. So do we want high temperature or do we want low temperature? Doesn't matter what we go for because we can easily change our reasoning later on. So let me start off with when temperature increases. That means at high temperature, when temperature is high, or temperature increases, what happened to the system? The system, which is the equilibrium, so you can say the system or the equilibrium will try to decrease the temperature. So how do you decrease the temperature? You will see and read back what you had just written for the first statement here, endothermic. Endothermic means you absorb the heat from your surrounding. So if you take in the heat from your surroundings and you want to help to decrease the temperature of the surroundings, I must make that very clear. So we increase the temperature on the outside to have high temperature on the outside. The system, which is the inside, tries to make the outside cooler, do the opposite to the change. It tries to make the outside cooler. But I only know how to absorb heat. So what do I do to make the outside cooler? I'm going to take away your heat. So I'm going to absorb more heat from the surrounding. But then we also have to read back our first statement. The forward reaction going from left to right, you would absorb heat energy. So when you absorb more heat, you will favor forward reaction. So to absorb more heat, therefore, you will favor forward reaction. And when you favor forward reaction, equilibrium shift to the right, you will get higher equilibrium yield of hydrogens. So very clearly there, the answer has got to be high temperature. High temperature there, or very high temperature, whichever one you choose. So when you absorb more heat from the surrounding, therefore the equilibrium shift to the right hand side. And when you shift to the right hand side, then you will favor forward reaction because you are going in the same direction as the forward reaction. It absorbs heat from the surrounding, absorb more heat from the surrounding in the same direction. Therefore, forward reaction is favored. And when you favor forward reaction, we will get more hydrogen. And that means the equilibrium yield of hydrogen is going to be higher there. In part 2, this is about pressure. So to explain pressure affects gases. That is the most important idea here. Pressure affects gases. So in terms of the behavior of particles, why do you use a high operating pressure? But they did say Le Chatelier principle suggests high pressure will produce a low yield of hydrogen in the first stage. Explain the behavior of particles, why instead we still use high pressure. So we don't ask on the equilibrium yield because we can see 1 mole of gas plus 1 mole of gas, that is 2 mole of gas on the left. And then how many mole of gas that we have on the right? We have 3 mole and 1 mole of gas. So we have 4 mole of gas on the left. On the right. So this means that if you have more gas on the left compared to on the right, and therefore what actually happens there is if you have high pressure, equilibrium try to lower the pressure, equilibrium will shift to the side which have lesser gaseous molecule, which is shifting to the left, and that is why it will have lower yield of ammonia, lower yield of hydrogen, I beg your pardon. So favor backward reaction there. But why in the world do we still use high pressure? Why in the world do we do that? This question is about rate. Rate is about how fast. So despite explain in terms of behavior of particles. So despite the lower yield of hydrogen at high pressure, we still need high pressure. We use high pressure so that we have fast enough of a rate of reaction. To have faster rate of reaction, that's the first key point there. Now, why in the world is the reaction faster in the presence of higher pressure? Well, that's what we need to explain in terms of collision theory. So at higher pressure, your gaseous reacting particles, the reacting particles are actually made to be closer together. They are compressed, they are squeezed closer together. And when they are closer together, so what can you comment about their collision frequency? So therefore, they will collide more frequently. As they collide more frequently, what can we comment about the successful collision? Therefore, more effective or more successful collisions. That means there are more particles that can overcome the activation energy. Therefore, rate increases. And that was the reason why we use the higher pressure despite the lower yield of hydrogen. The equilibrium yield is getting lower there. In part 3, we use a nickel catalyst. Why is the catalyst more effective when we cut it onto an unreactive honeycomb? So the unreactive there is not so important. The honeycomb is very, very important. So honeycomb structure. Renders or give the catalyst a much larger surface area, much bigger or much larger surface area. And these are surface area of the catalyst for your reacting particles to react on the surface, because this is talking about the solid catalyst. This is a transition metal, it's a solid catalyst. So it's in a different state. It's a different states of matter compared to your reactants, which are gases. Look at these state symbols, they're all gases, but your catalyst there is a solid. So you will learn more about this in A2 transition metals, A2 rate of reaction catalysis in the AQA syllabus eventually. So when you have a larger surface area for the catalyst to react, therefore faster rate of catalyzed reaction. We know we already have the use of a catalyst, so definitely the activation energy is lower. It's just that here it's not talking about lowering activation energy. It's about we already used the catalyst, we just want the honeycomb structure, faster rate of catalyzed reaction as reacting particles collide more frequently with the catalyst. Collide more frequently on the catalyst surface. And that is the reason why the reaction is faster, because there's more frequent collisions, there is more successful collisions, and they can react with a lower activation energy. So on the catalyst surface, there are more reacting particles. Reacting particles, faster rate of catalyzed reaction as reacting particles collide more frequently. So there are more reacting particles that can overcome the lower activation energy. That's the takeaway there. In part B, so what we have here is again Le Chatelier principle. So we want to talk about decrease in the pressure. So we count the moles of gas first. So as I did earlier already, there is 1 mole here and there is 1 mole there. So there are 2 moles of gases on the left. We focus on gases in our answer because pressure affects gases, versus there are 2 moles of gas on the right. Oh, this is a different reaction actually. So there is 1 mole there and there is 1 mole there. So 2 moles of gas on the left and on the right. So equal pressure on the both side. So equal number of molecules, equal pressure of gases on both sides. It means that changing pressure in this case decreasing pressure, but increasing pressure or decreasing pressure will have no effect, because you can't choose how to oppose the change because both sides have equal pressure. So changing pressure has no effect on this equilibrium position because both sides have the same number of moles of gas there, so no effect. This is no effect on the equilibrium yield because there is no effect on the equilibrium positions, so therefore also no effect on the yield of hydrogen since the position doesn't get affected at all. And that's it for that 9 marks overall first question there. In part 2, we have expression for Kc. Kc is to do with concentration, so I will do square bracket to represent the concentration of the product. I just take the product without the number in front because the number in front goes to the power. So it's SO3 concentration square divided by the concentration of SO2 square, because again the mole in front becomes the power, and then I am multiplying that by the O2 concentration at the bottom to the power of 1 there. In terms of the unit, so each square bracket represents mole per dm cube, so I have square term on top. I also have mole per dm cube square from the SO2 concentration square at the bottom, and you can clearly see that I cancel out the square and the square. So what am I left with? I'm left with 1 over mole dm minus 3. We gotta simplify that by having everything move out to the top. 1 divided by mole is mole minus 1. 1 divided by dm minus 3 is dm to the positive 3. You get 1 marks for doing the mathematics of the units correctly there. So in part B, so what we have is from this equation, so we need to think about this very carefully. So we might have to set up some equation here. So we have a volume of 1.40 dm cube. So the V total is 1.40 dm cube. And at equilibrium, so this is the mole at equilibrium, we have 0.0550 mole, and then we have 0.0720 mole of sulfur trioxide. And the thing is, Kc has the numerical value of 27.9. Find out the mole of the oxygen gas. Find out the mole of oxygen gas. Let this be X. So let this be X. So what I have is concentration at equilibrium is going to be X over the total volume, mole per dm cube, because we are just following the unit, mole per dm cube there. So here's also mole per dm cube. So just pressing your calculator, 0.0550 divided by 1.40. I get a lot of decimal places, 0.03929. And then 0.0720 divided by 1.40, I get 0.05143. So I can set up my equation earlier. I did already set up my equation earlier. The Kc is equal to concentration of SO3 square. So that is 0.05143, the whole thing square. Dividing that by 0.03929 square. And then X over 1.40 without any square because there is just 1 in front there. So the objective really is find X. So X over 1.40 equal to 0.05143 square over 0.03929 square. And then I'll multiply that by 27.9 at the bottom there. I move up the 1.40 to the top right hand side. So I will get 1.40 onto the other side because I move this up, and then I have 1.40 that I move to the top right hand side, and they're just pressing your calculator. 0.05143 square divided by 0.03929 square times 1.40, dividing that by 27.9. So what we get there is the mole of the oxygen. So we gotta learn about appropriate number of significant figures. Look at the data given. Oops, I meant to say 550 3 sig fig, 720 3 sig fig, 1.40 3 sig fig, 27.9 3 sig fig. So we have 3 significant figure data. So I'm gonna leave my final answer to 3 significant figures. I think it's best if I just write somewhere on the top there. So x equal to that. So x equal to 3 significant figure, 1 2 3. So 0.0860, 3 significant figure. End of that question there. In part C, we're going to repeat this experiment, same amount of the three things at the same temperature, but in a smaller flask. So temperature doesn't change, but the key thing here is temperature doesn't change. Only temperature can change Kc. So only temperature can change any equilibrium constant. So later on in A2, you will learn more about Kc, Kp, K whatever, Ka, Kw, a lot of equilibrium constant. Only temperature can change those. So it doesn't matter if you change pressure, if you change volume, it will not have any effect on equilibrium constant. However, is there any effect of using a smaller flask on the amount of sulfur trioxide? So smaller flask will mean smaller total volume. It means smaller volume. So how is pressure and volume related? Smaller volume of container. So as PV equal to constant, part of the ideal gas equation, then the pressure is higher pressure. So we have higher pressure. So as a result of higher pressure, what would your equilibrium do? So we got to count the moles of gases on the left. These were originally gases. So 2 plus 1 is 3 moles of gases on the left, 2 moles of gas on the right. So I got to write, how many moles of gas on the left. So 3 moles of gases on the left versus 2 moles of gases on the right. So what happened in terms of Le Chatelier principle? As pressure increases, your equilibrium will try to decrease pressure. So system tries to decrease pressure. How do you decrease the pressure? You will shift to the side with lesser gaseous molecule by shifting to the side with lesser gases. In this case, it will shift to the right-hand side, and therefore what is the effect on the amount of sulfur trioxide? Sulfur trioxide is on the right side. This is the product. This is on the right-hand side. As you favor the forward reaction, the lesser gases are on the right-hand side. You favor forward reaction, you will get more. So you will get higher amount, higher yield of your SO3 product there. And that's it for 3 marks, and that's it overall for that 9 marks question. I think I'll leave it there for these short tutorials on Equilibria topical questions. So thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. And do get in touch if you're interested in private tutoring, one-on-one or a very small group tutorials where I can go through any questions of your choice or any concepts that you wish to review. Thank you for watching again. Do share the channel widely with friends, chat group, juniors, seniors, relatives, and others. And I'll see you in the next tutorial video.